Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We are in chapter 10 where we are discussing the idea of scaling and renormalization. So let's briefly review what we did in the last lecture on scaling hypothesis. So the first point that we have seen throughout the course is that the universal properties at a critical point are described by quantities called as exponents, scaling exponents or critical exponents, and there are 6 of them: alpha corresponding to the specific heat, beta corresponding to the order parameter, gamma corresponding to the susceptibility, delta corresponding to the response at the critical point, nu corresponding to the correlation length, and eta is what we call as the anomalous dimension. The important thing that we know from experiments and all other information that we have is that continuous phase transitions, they will fall into different universality classes. Two very different systems, apparently very different systems or obviously very different systems, such as the liquid gas or the Ising magnet, their critical point are described by the same critical exponents, namely they fall in the same universality class and they have the same universal properties. The observation that we know about these systems is that the critical exponents are not independent and they satisfy certain relationships which are called scaling laws, irrespective of which universality class they are in. The scaling laws are the same. So to understand or to explain this, a hypothesis was made which is called the scaling hypothesis, which states that the singular part of the free energy is a generalized homogeneous function of its arguments. In addition to this, if you make a certain assumption or hypothesis, again called as hyperscaling, which is that the free energy density is simply determined by the correlation length, that is, free energy density will be 1 by correlation lengths to the powers of the spatial dimension, and this we know is certainly not true, but is certainly true in low enough dimensions, if you like. If you make this hypothesis as well, then you will see that all the scaling laws known in low dimensions can be derived, and you will find that the scaling laws such as the Rushbrook law, the Weidem law and the Fisher law, they do not depend on the spatial dimension, and the one that is provided by the hyperscaling relation does depend on dimension, and it connects the specific heat exponent to the exponent corresponding to the correlation length, and the spatial dimension explicitly enters this scaling law. So what is the upshot of this is that among the 6 critical exponents that we know, only 2 are independent. However, the scaling hypothesis does not tell us how to calculate these critical exponents. Moreover, there are some conceptual questions as to why we expect the singular part of the free energy to be a generalized homogeneous function. That was a well-informed hypothesis, but we would like to understand the physical underpinnings of this hypothesis. And again, as I mentioned, we do not have a method to compute these critical exponents, so that is definitely a problem that we need to tackle head on. So in this lecture, we will see one of the most important concepts that was developed in physics ever to be developed in physics, and this is the idea of the renormalization group. So how do we understand the fact that there is universality? How do we understand the fact that there are scaling laws? How do we understand the fact that different systems show the same critical behavior, that is universality? So let us begin by understanding what is the key idea behind the renormalization group. So to do this, I will ask you to recall what we observed when we solved the one-dimensional transverse field Ising model, the quantum model for its ground state. We solved it exactly by using Jordan-Wigner transformation, etc. And what we found was that at the critical point where you have a phase transition, you also have an emergent symmetry. And we made it a point to emphasize this while we are discussing this, that symmetry, at least at low energies, can be emergent. So this is an important lesson, and Kenneth Wilson, who worked on various problems starting from quantum field theory to classical statistical mechanics and everything in between, based on a variety of approaches, both field theoretic, numerical, etc., postulated a principle or an observation, right? And what Wilson said is that a system at its critical point has a new emergent symmetry, and this symmetry is scale invariance or dilatation invariance, right? So this is one single statement about the critical point. It states that at a critical point, the system has a new emergent symmetry, which is scale invariance. So I hope by the end of the lecture, you will see that just this one statement allows us to understand the origin of all the puzzles that we have encountered in the course. So this is the point I am making here, that this single principle, if you like, is enough to explain the behavior, the universal behavior, scaling laws and all of that. But you might wonder, right? So what do you mean by scale invariance? How do we understand what scale invariance means? Okay, and this is what we will explore in the next slide. So scale invariance is also called as dilatation invariance, and recall that when we discussed very early on in the course different types of symmetry transformations, we sort of for practical reasons classified them as arena symmetry transformations and internal symmetry transformations. So for example, a very standard arena symmetry transformation is translation. So you say that, okay, a system has, you want to implement the notion of some translational symmetry. What you can think of is you are somehow transforming the coordinates, you are maybe translating the system and changing the coordinates of the material points, and you can implement the symmetry as we have discussed. So then the fields will transform in a certain way, or the degrees of freedom will transform in a certain way, and so on. So the whole point is that the translational symmetry has some effect on the arena. So for example, if I do a translation, I can imagine, there are many ways to do it, I am just illustrating it by this simple equation here. The new coordinate of a point which was originally called x would be x plus a, where a is the amount by which you have translated. So the idea is that to describe this symmetry, we need a parameter called a, which is the amount of translation. So something similar is required for understanding the notion of a scale transformation or a dilatation transformation. So the first important observation or important thing that you should note is that dilatation or scale transformation is an arena symmetry, or it's some kind of arena symmetry transformation. So to describe this, we need a scale factor, and the scale factor is S, and this is the analog of this amount of translation A as far as scale transformation is concerned. Okay, and S is typically a non-negative number, and from the perspective of from the perspective of what we need to achieve in the course and so on, we will also typically work with S greater than 1, 1 being unity, the number 1. Okay, so S is some scale factor. So what is the action of S on the arena? So just for sake of concreteness, just imagine that S is 2. So what happens is, under the scale transformation, the new coordinate of a point whose original coordinate was x is scaled by S. That means the new coordinate will be x divided by S. Okay. Now you might wonder why it is defined like this. Okay, it's a convention. You could have defined it in a different way, but you could have called it Sx if you wish, but that's not important. This is a convention that we will follow, and there is a reason for this, because we are interested in what is called as coarse graining. We want to look at things on longer scale. So we want to demagnify if you wish. So if I had a lattice, I want to look at the system on a larger scale, right? So what does this mean? Something that was originally 2 meters will now be, in this new scaled version, in this x new, will become 1 meter, right? So in some sense we are coarse graining. That's what we are doing, right? So this is like, how do we draw a map of a country? Like if we want to draw a map of India, we can't draw this whole 3000 by 4000 kilometers, right? So we scale it and we draw it on a piece of paper. So we scale it, and therefore you see the very large distances are made into smaller distances and so on, right? And this is exactly this idea of the scale transformation. So it's very easy to understand what is scale transformation as far as the coordinates are concerned. But now the question is, how does the Hamiltonian, if you are thinking of some lattice problem, you can write down a Hamiltonian, or if you are thinking in terms of some Ginzburg-Landau theory, you will be writing its action S. So you have to then say, if I give you the scale transformation which changes coordinates this way, how is it that the Hamiltonian or the action, how is that going to get transformed? So for example, if we had some internal symmetry, we know how to do this, because what we will do is we will take this symmetry operation and we will act on the degrees of freedom, and you will get a new set of degrees of freedom, and then you will put it back into the action, and therefore you will see that there is a certain way we can encode the internal symmetry transformation. So what we need to do is, we need to figure out a way to implement the scale transformation on the Hamiltonian or the action as the context requires. So for now, what I am going to say is that I am going to formally assume that this can be done, and one of the great contributions of Wilson was to actually figure out how to do this systematically, which we will see in the course, of course. We will call this transformation as RS. Now there is no marks for guessing that R stands for renormalization group. So the renormalization group transformation with a parameter S. So H maps to a new Hamiltonian which we called as H prime, or formally RS takes H as an input, and it gives you a new Hamiltonian called H prime. You could as well implement this on an action such that in a Ginzburg-Landau theory, which we will do presently. S goes to RS of the S, and this is what we call as another action which is called as S prime. Okay. So when do we say that a system is dilatation invariant or scale invariant? We say that the system is dilatation invariant or scale invariant if RS of H turns out to be H, or if RS of the action is the same action for all S greater than 0. So how much ever you scale, you will come back to the same Hamiltonian. So this is when we say that a system has scale invariance or dilatation invariance. Okay. So what we have done is we have formally defined this scale invariance. Mind you, I have not told you how to actually implement RS of H. I have just taken for granted that such a definition is possible, and I'm now using this possibility to define when a system is scale invariant. So if you come up with a nice RS that will transform the Hamiltonian to a new Hamiltonian under the scale invariance, And if the new Hamiltonian turns out to be the old Hamiltonian, or the new action turns out to be the old action, then we say for any value of the scale factor, then we say that the system is dilatation invariant. Okay, let's explore this a little further. How do we implement this for a given system? Okay. So you will see that the implementation will strongly depend on what kind of system and model you are working with. So let's try to take our favorite model, which is the ON vector Landau-Ginzburg model defined by this action. So there is a field phi which transforms under the continuous ON symmetry, and I have some Lagrangian density which is written as L of phi, gradient phi, all possible gradients, etc. Although in our previous analysis we just kept only a few terms, we didn't keep all terms, but in principle all terms allowed by symmetry should be included in principle. So you might wonder, how can I handle this? So you say you find some scheme of naming the coefficients. So of course phi dot phi is a scalar and a scalar in the ON space, and therefore you should keep it because it's invariant under the ON transformation, and it has some coefficient A20. What is this 20? So this is a notation that we have just invented. It's not an ideal notation, but okay, it's some notation. 2 means that there are 2 powers of phi, 0 means there are no gradients involved in here. So you see this will be 40 because there are 4 powers of phi and no gradients involved. This is 2 powers of phi and it involves one gradient, in the sense it's not the power of the gradient, it involves one gradient and so on. So this will be 4, 1 and so on. So you can just cook up some notation for this kind of coefficients. And so the main message I want to convey to you is that an action like this can be thought of as a set of numbers such as A20, A40, A21 and A41 and all of that stuff, right? And you remember, for example, if I were to tune this coefficient A20 to negative values, then we claim that there is like you're in the ferromagnetic phase or something like that, if for example this were a real field. So what is the point is that this action is equivalent to some point in a space of these coupling constants. So you take all the coupling constants that are allowed, there could be infinite number of them, so this could be an infinite dimensional space, sure, right? So I'm just drawing it like a space here, and there are all these coefficients, so these are the axes corresponding to these coefficients, right? And you see that you can think of this action as if it is a point in the space. This point will be labeled by the coordinates, namely this A20, A40, whatever the values they have. Okay. Now, since we need some language that is commonly used, these kind of terms are also called as operators, right? So you will say that this is this Lagrangian is a sum of local operators. This is how people speak, especially coming from the quantum field theory side. And you can also think of these numbers that are multiplying these operators as defining the action itself, right? So you find a way to organize this series for the Lagrangian density, and you come up with some nice nomenclature for these coefficients, and you can collect them and collect them in some tuple if you wish, and that defines a point in some very high dimensional space, and that point P now describes the action, right? So this action S is equivalent to this point in the space of theories. So we think of this as a space of theories. All the theories here have the same Owen-Ginzburg-Landau structure. If for example certain quantities were negative, then you know that you could be in the broken symmetry phase, etc. Okay, so that's the idea of this approach. So you have come up with a way of characterizing theories as points in some very high dimensional space, and this is called the space of theories. So now we introduced in the 2 slides back that under the action of the scale transformation, S will become some new action. How can I understand this idea from the perspective of the space of theories? So S in the space of theories is some point described by some set of values of coefficients. Under the action of this scale transformation, you will get a new Owen-Ginsberg-Landau theory with all possible terms, but the coefficients of those terms will change, right? The values of the coefficients will change, and the values of the new coefficients will depend on this scale factor S, right? So what we can say is that the scale transformation induces a flow in the space of theories. Now what do you mean by that? So this is our original point defined by some set of A's, the coefficients A. I did one scale transformation, I will get a new point P1 here under the action of S1, that is described by a set of coefficients which depend on S1 and the initial point P, and if I do P2 it will find me another set of points and so on. So in some sense, as I change S, this sort of flows. So if I start with some other point, there will be another flow and so on. So what this is doing is, as I am scaling, as I am doing different values of this S, this point P flows in the space of theories, right? So another way of saying this is that this P prime Rs of P becomes a new point P prime, and that point will be characterized by a set of coefficients of the operators in the Lagrangian density, which are functions of S. So essentially the structure of the theory remains the same, the coefficients of the operators in the theory change under the scale transformation. Okay. So this is the idea, and if you start with the point P, and the point P can be any point in this, you will generate different trajectories of this, and that is why we call this flow, right? So it is like flow in, like if you have done like Hamiltonian dynamics, then you know that points in phase space flow via the Hamiltonian's equation, by the Hamilton's equations of motion. Quite similarly, this renormalization group transformation by a parameter S, which is analogous to time in Hamiltonian dynamics, will produce a flow of points in the space of theories. Okay, and this is why we use the word flow. Okay, all right. Okay, now let's explore the properties of this renormalization group transformation Rs. Okay, clearly if S is equal to 1, Rs acting on the action, I am not doing scale transformation is equal to 1 is I am not doing any transformation at all, I am just leaving the system unchanged. Rs of P must be equal to P, or if you talk in terms of the action, Rs when S equal to 1 of the action will be the same action. That is a statement that Rs of P is equal to P. Now I could ask, let's say that I want to do a scale transformation with S equal to 10. I could do one short scale transformation of S equal to 10. But I could also reach S equal to 10 by two different scale transformations. So I could choose S equal to 2, S1 equal to 2 and S2 equal to 5, and I could compose them, right? I could first do the 2 and then the 5, or I could do the 5 first and then 2 first and so on. And I have to demand, this is quite reasonable, that this composition should produce for me the S equal to 10 transformation. That is, if I had two scale transformation S1 and S2, if I compose them, I should get the transformation defined by S2 S1. S2 S1 is of course a number, so it doesn't matter whether it's called S1 S2 or S2 S1. And we just demand this property that RS2 of RS1P is equal to RS1 RS2P is equal to RS2 S1P. So in some sense we have an identity transformation, and we have a transformation which says that composition should produce a new transformation in a unique sense. Okay. So what this gives for us is what is called as a semi-group structure. Why semi-group and not group? Semi-group structure because we generally don't expect this to have an inverse. Why don't we expect to have an inverse? Particularly coming from the condensed matter perspective, we will be mostly interested in the S greater than 1 regime. That is, the scaling is always coarse graining. We are going to look at the system demagnifying it, if you wish. Right? We are going to look at systems on longer wavelengths. This low energies and longer wavelengths. And when you do that, you actually are going to lose information, if you wish, or keep only the most important information, is more precise way of saying it. And therefore, the inverse is not generally something that is expected to be meaningful. And this is why this renormalization group transformation is a semi-group transformation. Yet it is called renormalization group for historic reasons. And you may also wonder why it is called renormalization. Okay, that has also a historical baggage behind it, and it will take me a little effort to discuss that. So I will just request you to just imagine this to be a name given to this method, and we will, as we go along, we will see why the meaning of renormalization is, what exactly we mean by renormalization here. Okay, so this RS, which describes our scale transformation on the Hamiltonian, can be thought of as a transformation acting on a point in the space of theories, and it will take a point to another point, and it has to satisfy these properties. Okay, now comes an interesting additional concept. What is the fixed point of such a transformation? A fixed point of such a transformation, if I call this as P star, corresponding action for this will be called S star. So P star gives you a set of coefficients of the Ginzburg-Landau theory, if you wish, and there is an action you can construct, and under this renormalization group transformation with parameter S, for any value of S, you will see that RS of P star is P star. So using this definition of RS, we can now make a very important statement that when you find that under the renormalization group transformation with any scale parameter, the action doesn't change or the point in the theory stays fixed, that is called the fixed point, we say that the system is scale invariant. And Wilson's observation is that a critical system in this slightly refined language now is a fixed point of the renormalization group transformation. So in the space of theories, there are special points which will be fixed points of this renormalization group transformation. At that point, you will have scale invariance as an emergent symmetry, and the Hamiltonian comes back to it. And if you have a mathematical definition of RS acting, giving you a new Hamiltonian, given an input Hamiltonian, and you are able to find a Hamiltonian which doesn't change under RS for any S, then that point in the space of theories is a fixed, is a critical point. That is the one way of characterizing Wilson's statement within the language that we have introduced. Okay, now let us say that there is a fixed point, and let's explore what happens or what is the story near a critical point or a fixed point. Okay. So if P star is a critical point and RS leaves P star invariant, we can try to look at a point P. So this is P star. We can try to look at a point P which is close to P star. Now, of course, I have not defined any metric or any distance, notion of distance in P. So we can go with a more intuitive way of thinking about this. So it's somewhat, so you can imagine that this point P is some delta P away, and you can imagine the delta P is something small. Okay, so this is the story, and what we are going to ask is, under the action of renormalization group transformation, P will remain unchanged. P star will remain unchanged. How can we characterize what happens to P, or equivalently what happens to delta P, right? So what we are going to say is that Rs of P can be written as Rs of P star plus delta P. Okay, there is a small typo here. This should not be an exact equal to, it should be approximately equal to. So what we can do is, we can imagine that we are going to linearize, or we are going to sort of Taylor expand, if you wish, this transformation about P star. Why are we allowed to do this? Because Rs does not change P star. So we can say that Rs of P star plus delta P is P star plus some linear function of delta P. So the idea is that I have something in the neighborhood of P star. Under the renormalization group transformation, it will remain in the neighborhood. So if this is an infinitesimal, it will be again infinitesimally close by, but changed by a matrix, right? This is some huge matrix LS. That matrix depends on P star. It has properties of this critical point P star, and the parameter S also is involved in this. So this is like, I have some very complicated map in some very high dimensional space, and I am linearizing the map about some fixed point. Okay, note again that this equal to should not be, it's not a strict equal to, this is approximately equal to, right? And so what we are doing is, we are sort of saying that this is there is some matrix, some large dimensional matrix, which characterizes how this delta P changes. Okay, and this is exactly the statement I made. So if you started off something which is infinitesimally close to P star, under the action of Rs, it remains infinitesimally close by. That's what we mean by this, and we expect that this map from delta P to Ls of delta P is this is some matrix which characterizes this map. Okay, so this matrix Ls of P star is characterized, is in a sense a property of this critical point, and it depends parametrically on this scale factor S. Okay, all right. So now let us see Rs, we have seen now that Rs near P star is described by this matrix Ls of P star. So one way to think about this matrix and look at its properties is to diagonalize or try to find eigenvalues and eigenvectors of this matrix. Now, based on our discussions, we don't know whether this matrix is a Hermitian matrix or whether it's non-Hermitian matrix. In general, it may be a non-Hermitian matrix, right? So at least what we're going to do is, we're going to proceed by saying that, okay, it has some right eigenvalues and corresponding right eigenvectors. Okay, so let me label all its right eigenvalues by this index I, and say that there are some vectors in that space, right, and these are called eigenvectors of Ls. Eigenvectors are Oi, and the corresponding eigenvalue is S dependent, and that's why we call lambda I of S Oi. Okay, and these are also called as Eigen-operators, right? So this comes from the fact that they're the coefficients multiplying del square phi and all of that stuff. So the language that people have come to use is that they're also called as the Eigen-operators of this Ls. Okay, all right. So okay, there is another typo here. This is Ls of P star, right? These are Eigen-operators of Ls of P star. Okay, Now that we have postulated that this thing has eigenvectors and eigenvalues, I can expand this delta p, that is the excursion from the point p star, using this OI as a basis, if you wish. So I can write an arbitrary delta p in terms of GI OI. What are GI? GI are some numbers which characterize delta p, right? So all I am doing is I am finding a new way of bookkeeping my delta p using the Eigen-operators of my LS of p star. It's just a basis change. Okay. So this GI now describe how far away I am from the critical point. Okay. Now what we can do is we can say that I have postulated that this is the eigenvalue equation. So if I look at the action of LS of p star on delta p, I will see that this is LS of p star on this quantity, where delta p is now expanded in terms of this OI, and now you will see that this GIs will transform to GI times lambda I of S. So now you see we have found the flow equation for GI. So under the renormalization group transformation by a scale factor S, this GI will change and go over to GI times lambda I of S. And so the point is, the flow near the critical point is completely characterized by these quantities lambda I of S. That is the main message of this slide. So you linearize the renormalization group transformation about the fixed point, and so the derivative of that transformation is characterized by some kind of matrix which we call LS of p star. That matrix we posit to have eigenvalues lambda I of S, which depend on the parameter scale factor S, and it has some eigen-operators. Eigenvectors in this context are conventionally, or the field, people working in the field start calling them operators, right? And the idea is that the flow is now characterized completely by these parameters lambda I of S. Now what can I say about these parameters lambda I of S? That's what I would like to discuss next. Okay, so first is, remember all the properties of the renormalization group transformation that we used. So the first is, if S is equal to 1, then lambda I of S equal to 1 must be 1, because you see under the scale, if I do scale factor 1, GI will go to GI of lambda I of 1, but GI must remain unchanged because I'm not doing any scaling by 1 means I'm not doing anything. So lambda I of 1 must be equal to the number 1. Remember also that if I compose two scale factors like S1 and S2, if I do them one after the other, I should find the scale factor corresponding to S1, S2, right? It should be the transformation, the linearized map should be the matrix corresponding to S1, S2. If I take the product of these two matrices, first by S2 and then by S1, this must turn out to be the matrix that I would get if I do S1, S2. So this, if you just follow through, we will see that we will get equations lambda I S1 times lambda I S2 will be equal to lambda I of S1, S2. Now I claim that this is enough for you to show that if these conditions are satisfied, then associated with each eigenvector I, the indexed by I, there are numbers called as mu I such that lambda I of S is equal to S to the power mu I. Okay, I will state that again. If these conditions are satisfied, then you can show that lambda I of S is some power of S with an exponent mu I. Okay, and I invite you to show this. Okay, now that we have this formula for, remember we don't know mu I yet, we know that mu I exists. That's it. Okay. All right. Now, if with this development, what I can do is I can take LS and act LS of P star and act on delta P. Delta P is some arbitrary excursion that I had from the critical point, and I just do linear algebra now. So I hit this with this. This is our postulate that this delta P is characterized by some numbers Gi in the basis of the eigen-operators of Ls of P star. And under the action of Ls, this goes to lambda s. So this goes Gi s to the power mu I Oy. So what happens? Gi go to Gi times s to the power mu I. Now you see, we can classify these eigen-operators into three types. Okay, depending on the value of mu I. So first is that mu I can be positive. If mu I is positive under a coarse graining transformation, right? If I have coarse graining transformation means S greater than 1. If mu I is positive, you will see that S power a positive, S is greater than 1. So S power a positive number will start to, it will start to grow. And if mu I is less than 0, it will start to fall, right? And if mu I is 0, then I will not grow. Then this will be, if mu I is 0, this will be 1. So if mu I is positive, I have what are called as relevant operators. And if mu I is less than 0, I have what are called as irrelevant operators. And if mu I is equal to 0, they are called marginal operators. So remember, these operators are what we call as relevant or irrelevant and so on. And the mu I corresponding to the operator, if it is positive, is called relevant. So these operators grow under coarse graining, that their coefficients will start increasing under coarse graining, which means you will move away from the critical point. Irrelevant operators means that you will, under coarse graining, you will flow back. That is, they will flow back, meaning that it will come closer to, it will start losing strength. So as S becomes large, and if S is greater than 1 and if mu is negative, then that number will be smaller than 1. So in magnitude it will come down. And if it is marginal, it will remain unchanged. So we can classify the operators as relevant, irrelevant or marginal operators. Okay. Remember, at this stage we don't yet know what is the mu I corresponding to the operators Oi. All of this is formal. We are just saying that the operators will come in three types. They are relevant, irrelevant or marginal. Okay. So let's understand. So imagine that this is I have just schematically drawn here the space of theories. So these are the coefficients, it's abstractly written as M1, M2 for this axis. There are many axes like this, and all of them have different values of M1 and M2 and so on. So imagine that P star is one of the critical points, and this direction here is some operator O, let's call it 1, and the way I have drawn this flow diagram is that if your delta P was here, right, where this red marker is, the mouse pointer, if it is here, and if this direction were, if this O1 operator were irrelevant, then under the renormalization group flow, it will just flow back as I am increasing S, it will come and it will sit here and it will go to this part, it will come back and sit at the point P star. But what happens if I am in this red direction here? So this is some another operator which let's call it O2, and there is a mu2 associated with this which is positive. So if I start with this, s is greater than 1, so s to the power mu2 will be something greater than 1. So I will move further away and further away and further away and so on. So this is a relevant operator. So if I have some weight, or if my delta p is such that there is a piece in this relevant direction, then I will start moving away from the critical point. Okay, all right. Now comes the central idea of how universality emerges. Universality emerges from the fact that at critical points, it turns out that only a few operators, like 1, 2 or 3 maybe, are relevant. It depends on what is the nature of criticality. Like for example, in the standard critical points that we have, there will be only 2 relevant operators. All other operators in the theory, like remember, look at the Ginzburg-Landau theory that we wrote down. You can write all kinds of terms. You can write phi squared terms, you can write phi to the 4 terms, you can write gradient phi whole squared terms, you can write phi to the 6 terms, you can write gradient square phi the whole square terms, you can write all of these terms. They all have coefficients. All of them, most of them turn out to be irrelevant at the critical point, like of interest, right? That means only certain parameters in the action corresponding to the relevant operators govern the physics near the critical point. So for example, when we discussed the Ising model very early on in the course, we said we could write down next neighbor interactions, we could write down 4 spin interactions, etc. So you could think about them and you can convince yourself that all of those extra things, that bells and whistles that you can put in, turn out to be irrelevant at the Ising critical point. And this is why, irrespective of what kind of system is realizing this Ising transition, it seems to forget a lot of the details and only the essential things which define the relevant directions control the critical phenomena, and you get universality. Okay. So this is of course sounding a little abstract, but we will see this concretely in calculations as we go along. Okay. So what have we done? We have first argued that within the renormalization group framework, we classify operators near a critical point as relevant and irrelevant, and we observe, okay, you have to do calculations and look at examples to see why we observe this, that there are only a few relevant operators and we understand universality. But can we understand what is the origin of scaling laws, and can we understand what is the origin of the generalized homogeneous function nature of the free energy? Okay. So let's again go back to this Ginzburg-Landau model, ON Ginzburg-Landau model, and we have postulated that there is something called RS, and RS of S, the action, goes to some new action. And in terms of the point in the space of theories, RS of P will be a new point P prime. Okay. So now we are just simply doing a scale transformation. So nothing should happen to our partition function, right? So the partition function viewed in the original system or in the transformed system is the same. Now, if I think of working with a system with periodic boundary conditions and think of having a system with volume V or something like this, then under the scale transformation, if you had done it with a finite volume, you will see that the new volume is related V prime related to the old volume by S to the power V by S to the power D. This is simply coming from the definition, right? That means if I take T times, okay, negative log of this partition function, I will get some free energy density which now depends on the parameter via some function, which is a function of now many parameters, all the coefficients that are going into the Ginzburg-Landau theory. So those coefficients are described by this P, the point P. So because the partition function is unchanged, you will see that V times f of p, the free energy density, is V prime times the same function, because you see this partition function integral as the only difference is that instead of coefficients of p, the coefficients are p prime, right? So this function is the same function. So now because the V prime and V are related by the scaling relation, you will see that f of p is equal to s to the power minus d f of p prime. Okay. So this is the result that we have. And what does this mean? If I now take the thermodynamic limit, the V's drop out, right, because I have cancelled the V's. This equation is valid also in the thermodynamic limit in the infinite volume system. I see that f of p is related to s to the power minus d f of p prime. Okay, very good. Now, let us imagine that this point P was close to a critical point. So, let us say that is P star. Therefore, we know how to parameterize this. We know that P can now be parameterized by delta P, which is like the small vector connecting P star and P. So, what we can imagine is that the free energy is function of delta P, which is a completely reasonable thing to do. But using this expression now, we see that f of delta P is equal to s to the power minus d f of that matrix, the linearized version of Rs, this matrix acting on delta P. But now we know that delta P can be written in terms of Gi, the coefficients of delta P in the basis of the eigen-operators of Ls of P star, and therefore this is a function of all these variables. That is why it is a set of Gi times s to the power Gi, but we know Gi transforms under Ls of this to s to the mu I Gi, right. So there are a huge number of parameters Gi, but now you realize something very important. We need to keep only the relevant operators here, because the irrelevant operators where mu I are negative, as you keep increasing s, will just go to 0. The coefficients will go to 0 because s is a number greater than 1. We are coarse graining and we are taking it to the negative power, so it will keep decreasing in magnitude and it will go to 0. So essentially, if you do if you do the renormalization group transformation a lot of times, you will see that all the irrelevant operators drop out, and near the critical point, the free energy will be a function of only the few relevant operators that are remaining. And here is the remarkably beautiful result. This free energy, which is now a function of these few relevant parameters, is also a generalized homogeneous function of its parameters, and this is explicitly shown by this equation, and that is f of g is s to the power minus d times s to the mu I by times gi. So if you do a scale transformation, there is a way to rescale out by s to the power minus d to get the same free energy. So what Wilson's theory tells you is that the scaling hypothesis is coming out as a theorem of Wilson's starting point, which is that the system has scale invariance. So if the system has scale invariance, namely the single idea that at the critical point the system has an emergent symmetry called a scale invariance, from that single idea we are able to show that the scaling hypothesis comes out as something that scaling hypothesis can be inferred from this. So Wilson's observation gives rise to scaling laws. Okay. So we have understood where universality comes from, and we have understood where the generalized homogeneous nature of the free energy comes from, and from there we are also able to see that it has to satisfy scaling laws. Okay. Okay. So I will be the first to admit that many abstract sounding notions have been introduced in this lecture. So what we will do is we will summarize these ideas now, and we will start doing calculations using these ideas, and you will see that all these abstract ideas can be better understood by working through examples. Okay. But before we do that, let me just summarize what we have done. So Wilson's renormalization group idea addresses the puzzle coming from scaling hypothesis. Why is the free energy or the singular part of the free energy a generalized homogeneous function of its parameters? How do we find the critical exponents? So Wilson made the statement that everything, quote unquote everything, meaning all aspects associated with universal phenomena, etc., can be understood based on a single concept. We introduce one single idea into the game. It's like a principle. A system at criticality has an emergent symmetry called scale invariance. If you insist this point, that all critical points have to satisfy this condition, then you will see that all else follows in a sense. So to do this, we have to introduce the notion of what do we mean by scale invariance. So for this, we have to define a scale transformation, and that is defined by a scaling factor. And in the context of our interest, you will see that the scaling factor is typically more than 1, which means we are coarse graining, right? Okay. So we use the scale transformation notion to postulate that the action of the system will change from S to S prime by some kind of function defined by the parameter S, called as the renormalization group transformation with subscript S, or S of the action. It gives me a new action. And we also said that we can think of this, at least within the Ginzburg-Landau framework, we can think of each action as if it's a point in a space of theories, where that point is described by the coefficients of the operators in the Ginzburg-Landau Lagrangian density. Okay? And we can think of the scale transformation as producing a flow in the space of theories. Then within this framework, we realize that the critical point is a fixed point of this renormalization group transformation, which means that the fixed point is insisting that it is a scale invariant point or a scale invariant action. In the vicinity of this fixed point, we were able to linearize RS, and we said that the action of RS is captured by a matrix, a big matrix, which depends on the parameter S, and its eigenvalues are characterized by these exponents mu I, and corresponding eigenvectors are called Eigen-operators. And those operators can be classified as relevant, irrelevant, or marginal. Relevant operators grow, the coefficients of the relevant operators will grow upon coarse graining. The coefficient of irrelevant operators will die upon coarse graining, and marginal operators will stay unchanged. And the main idea of universality emerges from the fact that there are, in any critical point, there will be only a few relevant operators, right? So for example, in the Ising kind of transition that we will be studying, in the Ising critical point, you will find that there are only 2 relevant operators, and that is the temperature and the magnetic field. Okay. All right. Based on this, and using simple ideas about partition functions and the connection to free energy, etc., we were able to show that the free energy density near a critical point will be governed only by the parameters associated with the relevant operators, and that it is a generalized homogeneous function of these relevant parameters. So in a sense, we were able to derive the fact that the free energy density is a generalized homogeneous function of its parameters. So what we effectively did was we actually derived the scaling hypothesis from Wilson's principle that there is scale invariance at a critical point. Okay. So now the question is, we can pose what we need to do further very concretely. How do we find a real implementation of RS that allows us to compute the values of these mu i's? Remember, if we get mu i's, we have solved the problem, in the sense we can get all other results in terms of mu I. That's exactly what we have seen. So we need to find a way to implement RS in various problems, right? So Wilson himself came up with a very nice way of doing it in a very that is applicable to a variety of situations. But we will start with what is called as real space methods. So we'll start with lattices, and we will show how to implement RS on a lattice, and that is what we will do in the next lecture. And I'm sure that you will be dying to know how to do this, and maybe you could even try it yourself. And please do join me for the next lecture, so that we can exchange notes maybe, and you can see whether the ideas that you had are similar to what was done by very thoughtful people in the past. So thank you, and see you in the next lecture. Namaskar.